186,282 miles per second, the fastest speed reality allows. Fast enough to circle Earth 7 times in a heartbeat. Fast enough to reach the moon in seconds. Fast enough to cross the distance from the sun to Earth in minutes. And yet, on the scale of the universe, it's painfully slow. At light speed, crossing our own galaxy would take 100,000 years. Not the universe, just our local neighborhood. And while light has been traveling since the Big Bang, 13.8 billion years non-stop, vast regions of the cosmos are still too far away for their light to ever reach us, which means this isn't just a speed limit, it's a prison. The real question is no longer how fast can we go, but how much of the universe is already lost to us forever. Let's begin. Part 1. The deceptive slowness of light speed, the shocking truth revealed. 186,282 miles per second. That's light speed, fast enough to loop around Earth 7.5 times in a single second. Fast enough to reach the moon in just over 1 second. Fast enough to travel from the sun to our planet in merely 8 minutes. For generations, we've labeled it the universe's ultimate speed limit, the fastest phenomenon in existence. Unbeatable, absolute, the cosmic champion. But here's what nobody tells you in textbooks. On a universal scale, light speed isn't remotely fast. Actually, it's so slow, so incredibly, maddeningly, impossibly sluggish, that it renders the entire cosmos essentially inaccessible to us. Think about that for a moment. The fastest thing we know of, and it's still not fast enough. According to Universe Today, a premier science publication, at cosmic distances, light speed becomes incredibly, annoyingly, frustratingly slow, and Scientific American backs this up completely. Their research shows that while light speed appears amazingly fast to humans on Earth, when you're talking about interstellar space, it's glacially slow. Even reaching the closest star requires more than 4 years. Let me break this down in terms you can actually wrap your mind around. If you could somehow travel at light speed, the absolute cosmic speed limit, the fastest velocity anything can possibly achieve, according to physics, it would still consume over 100,000 years to cross our own galaxy, our home galaxy. 100,000 years, at maximum possible speed, just to cross our neighborhood in space. And here's the kicker. Our galaxy represents just one among billions. The observable universe has expanded so enormously that light itself, despite racing outward for 13.8 billion years since the Big Bang, hasn't even managed to reach us from the most distant regions we can theoretically observe. The universe is playing a cruel joke on us. Over the next 2,000 words, we're going to dig into exactly why light speed feels so devastatingly, heartbreakingly inadequate when compared to the actual scale of space. We'll examine distances you can comprehend, journeys inside our solar system. Then we'll push outward to nearby stars. After that, we'll confront neighboring galaxies, and ultimately, we'll face the true magnitude of the observable universe. By the end, you'll grasp why certain physicists describe light speed as the great cosmic joke, why the universe appears almost deliberately engineered to be unreachable, and why, despite being the speediest phenomenon we've documented, light itself remains trapped in a cosmos too vast to ever fully traverse. Now, you might be wondering, how can the fastest thing in the universe be too slow? Isn't that a contradiction? Stay with me, because the answer will fundamentally change how you view space, time, and our place in this massive cosmos, the solar system, where light speed still looks impressive. Let's begin close to home. Within our solar system, light speed actually delivers impressive results. The Sun sits roughly 93 million miles away from Earth. That sounds like an enormous distance, right? But light covers it in merely 8 minutes and 20 seconds, less time than it takes to brew a pot of coffee or watch a couple YouTube videos. Consider this reality for a second. When you look at the Sun right now, and please don't actually stare at it too, observing it as it appeared 8 minutes ago. If the Sun suddenly vanished, ceased to exist, we wouldn't realize it for 8 full minutes. For 8 minutes, we'd continue living our lives, completely unaware that our star had disappeared. Mars, during its closest approach to Earth, sits about 34 million miles distant. Light requires roughly 3 minutes to travel from Earth to Mars. This means when NASA engineers transmit commands to Mars rovers like Perseverance or Curiosity, there's a 3-minute transmission delay. Engineers send a command, wait 3 minutes for it to arrive on Mars. The rover executes the instruction, and then they wait another 3 minutes to observe the result through transmitted data. A 6-minute round trip for information. Frustrating for mission control, sure, but definitely manageable. You could grab a snack and be back before the response arrives. Jupiter orbits at approximately 484 million miles away. Light takes about 43 minutes to reach the gas giant, still fast enough that scientists can communicate with spacecraft like Juno orbiting Jupiter without excessive frustration. Less than an hour. You could watch a TV episode while waiting. But then we venture to the outer solar system, and things start getting uncomfortable. Neptune, our solar system's most distant planet, orbits at an average distance of 2.8 billion miles from the Sun. Light requires for hours and 10 minutes to reach Neptune. That's starting to feel genuinely slow, isn't it? Imagine transmitting a message to a spacecraft orbiting Neptune and having to wait over 8 hours for any response. You could work a full shift, go home, eat dinner, and still be waiting. Compare this to texting a friend across the country, instant email to someone in Japan. Seconds, but a message to Neptune, half a workday, one direction only. And then there's what we consider the edge of our solar system. The Voyager 1 spacecraft, launched way back in 1977, over 45 years ago, currently ranks as humanity's most distant artificial object. It's traveling at roughly 38,000 miles per hour, and it's now about 15 billion miles away from the Sun. That's 159 times farther from the Sun than Earth is. Think about that ratio for a moment. Light takes 22 hours and 30 minutes to reach Voyager 1. Nearly a complete day, almost an entire rotation of our planet, just to cross what we consider our cosmic backyard, our immediate neighborhood in space. But here's where things get really interesting. I mean existentially troubling. Are you ready for this? Because this is where the illusion of light speed's adequacy completely shatters. Our solar system, this massive collection of planets and moons that takes light nearly a full day to cross, is absolutely tiny compared to the distances between stars. The nearest star to our Sun, a red dwarf called Proxima Centauri, sits approximately 25 trillion miles away. Not billion, trillion, with a T. At light speed, that journey consumes for 0.24 years. Not for hours, not for days, not for months, for years and 3 months. Longer than a college degree, longer than a presidential term. And that's just to reach our closest neighboring star. The one literally next door in cosmic terms. The nearest stars, where disappointment begins. Let's explore Proxima Centauri in greater detail, because this is precisely where you begin understanding just how inadequate light speed truly becomes. Proxima Centauri forms part of the Alpha Centauri system, a triple star arrangement that represents the closest stellar neighbor to our Sun. At 4.24 light-years distant, it's literally the closest we could possibly get to another star system, our absolute nearest option. And yet, traveling at light speed, the journey would consume over 4 years. 4 years. Think about what that means in practical, human terms. If we transmitted a light-speed message to an alien civilization inhabiting a planet orbiting Proxima Centauri, and they immediately responded the instant they received it, we wouldn't get their reply for 8.5 years, nearly a decade for a single conversation exchange. One question, one answer. If you sent that message at age 20, you'd be pushing 29 by the time you received their response. And that's assuming they responded instantly, with zero delay for consideration or translation or debate about whether to respond at all. According to Scientific American, even reaching this nearest star requires more than 4 years at light speed, making interstellar distances glacially slow to traverse. Glacially, as in slower than ice ages. But wait, it gets substantially worse. Proxima Centauri happens to be unusually, exceptionally close to us. Most stars sit much, much farther away. We got lucky with our nearest neighbor, or did we? Because even this lucky proximity is devastatingly far. Sirius, the brightest star in our night sky, the one you can easily spot on clear winter nights, sits 8.6 light-years away. That's over 50 trillion miles. A light-speed journey would require 8.6 years. A round-trip message exchange would consume 17.2 years. You could send a message as a high school freshman and receive a response just in time for your 10-year reunion. Vega, another prominent bright star, sits 25 light-years distant. A message sent there when you were born wouldn't arrive until you celebrated your 25th birthday. If they responded immediately, you'd be 50 years old, middle-aged, possibly with kids of your own by the time you heard back. Your entire young adulthood would pass in the time it takes for one exchange. And these stars are all nearby. Stars we can observe with our naked eyes on clear nights. Stars that feel close when we gaze upward at the night sky and pick out familiar constellations. The average distance between stars in our region of the galaxy measures about 5 light-years, so Proxima Centauri is actually pretty typical in terms of stellar spacing. But our galaxy itself, it spans 100,000 light-years, from edge to edge. Let that number settle in your mind for a moment. If you found yourself at one edge of the Milky Way and wanted to travel to the opposite side at light speed, the absolute fastest possible velocity in the universe, the journey would consume 100,000 years. Human civilization has only existed for roughly 10,000 years. We've only had writing for about 5,000 years. We've only had the internet for about 30 years. At light speed, you couldn't even cross your own galaxy within the entire span of recorded human history. Not even close. You'd need 10 times that duration. Think about everything humanity has accomplished in 5,000 years. From ancient Sumeria to smartphones. From cuneiform tablets to quantum computers. From pyramids to space stations. All of that progress, all of that time, and you'd only be 5% of the way across the galaxy at light speed. So when scientists talk about interstellar travel, when science fiction shows depict starships casually jumping between star systems, when we dream about exploring the galaxy, we're not just talking about building faster rockets. We're not talking about better fuel or more efficient engines. We're talking about overcoming a fundamental limit that makes the entire galaxy effectively unreachable using any physics we currently understand. And our galaxy, It's just the beginning. It's just our local neighborhood. There are billions of other galaxies out there, each containing hundreds of billions of stars. How long would it take to reach those at light speed? Stay tuned, because the numbers are about to get truly mind-breaking. And honestly, a little terrifying when you really contemplate what they mean for humanity's future in space. But before we zoom out to those galactic scales, ask yourself this. If light speed is this inadequate for reaching nearby stars, what does that say about our chances of ever becoming a truly spacefaring civilization? What does it mean for the possibility of contacting alien life? And what does it reveal about our place in this vast, lonely cosmos? The answers might surprise you, or maybe they'll just make you appreciate Earth a little bit more. Part 2. The galactic scale of impossibility. Our galaxy, an ocean we can never cross. The Milky Way galaxy represents our home, our cosmic address. It contains somewhere between 100 billion and 400 billion stars, along with countless planets, moons, asteroids, comets, and other celestial objects we haven't even discovered yet. The galaxy takes the shape of a disk with elegant spiral arms and a dense central bulge. That disk measures approximately 100,000 light-years in diameter and roughly 1,000 light-years thick at most points. Imagine a cosmic pancake spinning through space, and you've got the basic shape. We're positioned about 26,000 light-years from the galactic center. That means the light we observe from the core of our own galaxy is 26,000 years old. When astronomers point their telescopes at the galactic center, they're witnessing it as it appeared during the Stone Age on Earth, when humans were still painting on cave walls and hunting woolly mammoths. That light was just beginning its journey toward us. Here's a thought experiment that'll really mess with your head. Imagine you could board a spacecraft tomorrow that travels at light speed. Pure science fiction, impossible according to current physics. But let's pretend. You point it toward the galactic center and hit the accelerator. You travel for 100 years straight. An entire century passes. You've covered 100 light years, just 0.1% of the distance. 1/10 of 1%. Barely a dent. You travel for 1,000 years, a period longer than all of recorded human history. Longer than Christianity. Longer than the Roman Empire. Longer than any nation has existed. You've covered 1,000 light years, just 1% of the distance. 1%. You travel for 10,000 years longer than human civilization has existed, longer than agriculture, longer than cities. You've covered just 10% of the distance. You'd need to travel for 26,000 years to reach the center of your own galaxy, your home galaxy, the cosmic neighborhood you were born in. And remember, this assumes you're traveling at the absolute maximum speed the universe allows. This isn't if we had better rockets, or if we discovered new propulsion technology. This is if we somehow achieved the theoretical maximum velocity permitted by the laws of physics themselves. And it still requires 26,000 years just to reach the middle of our own galaxy. Not the far edge, just the center. Now let's say you wanted to truly explore the galaxy, not just reach the center, but actually visit different regions. Observe different star systems, explore diverse planetary environments, study various stellar phenomena. The galaxy possesses a volume of roughly 8 trillion cubic light-years. Even if you only wanted to visit a tiny representative sample, let's say 1 star per cubic light-year, which is actually far less dense than reality, you'd need to travel trillions of light-years total. At light speed, that would consume trillions of years. With 80 trillions, the current age of the universe, stands at only 13.8 billion years. That's billions with a B. You could have started exploring the galaxy at the precise moment of the Big Bang itself, traveled at light speed non-stop without ever slowing down or resting, and you still wouldn't have observed even a tiny fraction of 1% of the galaxy. Not 1%, a fraction of 1%. The galaxy is that massive. Light speed is that inadequate. But waiter, probably thinking, okay, so exploring the whole galaxy is impossible. But what about just our neighborhood? The stars around us? Great question. Let's zoom in and make this even more depressing. The stellar neighborhood, our cosmic prison. Astronomers have a term for the region immediately surrounding our sun. They call it the solar neighborhood, or sometimes the local neighborhood. It sounds friendly, doesn't it? Neighborly, like you could pop over and borrow a cup of sugar. This region measures roughly 100 light-years across, centered on our sun. It contains approximately 400 stars, a tiny, microscopic fraction of the galaxy's total stellar population. But the region we've studied most extensively, the stars we know best, our immediate cosmic neighbors. These 400 stars represent our cosmic neighborhood, the stars closest to us, the ones we've examined in the most detail through telescopes, the ones where we're actively searching for exoplanets and potentially habitable worlds that might harbor life. At light speed, it would require 100 years to cross this neighborhood, to visit your immediate neighbors in space. 100 years, an entire human lifetime, just to traverse your local area, your cosmic zip code. But let's get more specific. Let's discuss some notable stars in our neighborhood and how long reaching them would take at light speed. Because specific examples make this real in a way that abstract numbers can't quite capture. Barnard's star, 5.96 light-years away. Nearly 6 years of continuous travel at maximum possible speed. 6 years to reach a star we can observe through modest telescopes. Wolf 359, 7.86 light-years, almost 8 years. You could start the journey as a newborn and arrive just in time to begin elementary school. Lalande 21185, 8.31 light-years. Most of a decade spent in transit to a star system we barely understand. Lytton 7-6-8, 8.73 light-years. Nearly 9 years. A full pregnancy lasts 9 months. This journey lasts 9 years. Ross 154, 9.69 light-years. Nearly a decade of travel. You could start this journey in high school and arrive just after your 10-year reunion. Epsilon Eridani, 10.5 light-years. This one's particularly notable because it resembles our sun and astronomers believe it might host planets in its habitable zone. Over 10 years to reach it at light speed. Over a decade to our most promising nearby candidate for another Earth-like world. Tau Ceti, 11.9 light-years. Another sun-like star with potential planets that astronomers get excited about. Nearly 12 years of travel. You could start the journey when your kid is born and arrive just in time for their middle school graduation. And these are the close ones. These are the stars we consider nearby when we talk about potential interstellar missions or SETI searches or future human expansion into space. Now here's the absolutely crushing reality that keeps astronomers up at night. If humanity decided tomorrow to become an interstellar species, to spread out among the stars like we've spread across Earth and we somehow invented light-speed travel through some miraculous breakthrough, here's exactly what that would look like in practice. We send a colony ship to Proxima Centauri carrying 1,000 colonists, supplies, equipment, everything needed to establish a new civilization. It takes 4.24 years to arrive. The colonists immediately start sending messages back to Earth, reporting on conditions, sharing discoveries, requesting additional supplies or information. Those messages take another 4.24 years to reach Earth. By the time Earth Mission Control knows whether the colony succeeded or failed, nearly 9 years have passed. 9 years of uncertainty, 9 years of waiting, 9 years wondering if your friends, family members, colleagues are alive or dead on a distant world. We send another ship to Barnard's star. Nearly 6 years of travel, 12 years round trip before we hear whether they survived the journey and established a viable colony. We send ships to a dozen nearby stars. Each journey consumes years. Each message home requires years. Each question asked of Earth takes years to answer, within a single human lifetime assuming. We started right now with perfect light speed travel. We could maybe, possibly establish colonies around 10 or 15 nearby star systems. Maybe 20 if we really pushed it and got lucky. And remember, there are 400 stars just in our immediate neighborhood alone. To colonize even this tiny region of space would require centuries, thousands of years, realistically. Generations upon generations of colony ships, each taking years to reach their destinations, each establishing footholds that would eventually send out their own colony ships to even more distant stars, and the neighborhood itself. It represents just 0.0001% of the galaxy. 4 zeros after the decimal point. Essentially nothing. You could spend 10,000 years colonizing the solar neighborhood at light speed, and you'd have explored a rounding error of the Milky Way. A cosmic footnote. A barely measurable fraction of what's out there. Think about the implications of this for a moment. Really let it sink in. If light speed, the universe's ultimate speed, limit is this inadequate for exploring just our immediate galactic neighborhood, what does that mean for the grand visions of galactic civilizations we see in science fiction? What does it mean for humanity's long-term survival prospects if Earth becomes uninhabitable? Where exactly would we go? The answers get worse, much worse. Because now we're going to zoom out even further. Other galaxies, forever out of reach. If our own galaxy feels unreachable at light speed, other galaxies exist in a completely different category of impossible. We're not talking difficult, we're not talking challenging, we're talking functionally impossible on timescales that matter to any civilization. The nearest major galaxy to the Milky Way is Andromeda. You've probably seen pictures of it. It's beautiful, spiral-shaped, massive, on very dark, clear nights, far from city lights. You can even spot it with the naked eye as a faint smudge. Andromeda sits 2.5 million light-years away. 2.5 million years of travel at light speed. Let me provide some historical context to make this number comprehensible. Because your brain literally cannot process what 2.5 million years actually means without reference points. 2.5 million years ago on Earth, modern humans didn't exist yet. Homo sapiens wouldn't appear for another 2.2 million years. Homo erectus was just beginning to appear in Africa. Our direct ancestors were just figuring out how to walk upright and use primitive stone tools. If a light-speed spacecraft had departed Earth 2.5 million years ago heading toward Andromeda, it would be arriving right now, today, this very moment. And the travelers aboard, if they had somehow survived in perfect suspended animated wood, returned to find that humanity had evolved from primitive ape-like creatures, developed complex language, created civilizations, invented writing, built cities, fought wars, composed symphonies, painted masterpieces, split the atom, and developed space travel while they were gone. The entire story of humanity, from beginning to end, would fit inside that single one-way journey. Every empire that ever rose and fell, every innovation, every revolution, every love story and tragedy, all of it. And you'd still only reach the nearest major galaxy. And Andromeda is the closest major galaxy to us, our nearest galactic neighbor of comparable size. The Large Magellanic Cloud, a satellite galaxy that orbits the Milky Way like a moon, sits 163,000 light-years away, still impossibly, devastatingly far. You'd need to travel longer than modern humans have existed just to reach this small satellite galaxy. The Small Magellanic Cloud sits 200,000 light-years distant, 200,000 years at maximum possible speed just to reach a small dwarf galaxy orbiting ours. But these galaxies all form part of what astronomers call the local group, our galactic neighborhood. The local group contains about 80 galaxies, most of them small dwarf galaxies barely worthy of the name, spread across a region approximately 10 million light-years in diameter. At light speed, crossing from one side of the local group to the other would consume 10 million years. 10 million, that's longer than human ancestors have existed. That's longer than most mammal species survive before going extinct or evolving into something else. And the local group represents just one small cluster in a vast cosmic web of structures, the Virgo supercluster, which contains the local group along with thousands of other galaxies, measures about 110 million light-years across. 110 million years to traverse at light speed. The Laniakea, the even larger structure we're part of that contains multiple superclusters, spans approximately 520 million light-years across. These numbers are so enormous, they lose all meaning. They become abstract. Your brain simply cannot process what 520 million years actually represents. It's longer than complex life has existed on Earth. It's longer than Earth itself has existed in its current stable form. It's longer than the solar system has had its current arrangement of planets. And these structures exist in what we consider our cosmic neighborhood, our local region of space, the relatively nearby universe, according to research on cosmic distances and light speed limitations. Even with the speed of light, which appears incredibly fast to humans, interstellar and especially intergalactic scales remain glacially slow to traverse. Glacially, not just slow, glacially slow. The observable universe measures approximately 93 billion light-years across. If you started traveling at light speed from one edge of the observable universe, pointing yourself toward the opposite edge, do you know how long that journey would require? 93 billion years. The universe itself has only existed for 13.8 billion years. Not even 15 billion. Just under 14 billion. Let that paradox sink in for a moment. Really contemplate what it means. The universe has expanded so dramatically, so enormously since the Big Bang that it's now larger than light. Could have traveled even if it had started at the moment of creation and traveled non-stop until now. Even traveling at the cosmic speed limit, the absolute maximum velocity the laws of physics permit. You could not cross the observable universe if you had started at the Big Bang itself and traveled continuously without rest until this exact moment. You'd only be roughly 15% of the way there. 15%. After nearly 14 billion years of continuous travel at maximum speed, the universe expanded faster than you could cross it. Space itself grew faster than light could traverse it. Light speed isn't too slow because light itself is inadequate. Light speed is too slow because the universe is unimaginably, incomprehensibly, almost mockingly large. It's like the universe is taunting us, showing us countless galaxies through our telescopes, revealing billions of stars and trillions of planets, displaying cosmic wonders beyond imagination, and then quietly whispering, "But you'll never reach any of it. Ever, no matter how hard you try." So when you look up at the night sky and see those distant stars, those faint smudges that are actually entire galaxies, remember this: you're not just looking at distant objects. You're looking at places you can never visit, destinations forever beyond reach, wonders you'll observe but never touch. And it gets even worse, because the universe isn't just large, it's large and expanding, and that expansion is about to make everything we've discussed so far seem almost optimistic by comparison. Ready to have your mind completely blown? Because part 3 is going to reveal why even these impossibly vast distances we've discussed actually understate the problem. The universe isn't just unreachable because it's big, it's unreachable because it's actively running away from us, faster than light itself. How is that possible? How can anything move faster than light? Stay tuned, because the answer will fundamentally change how you understand space, time, and the ultimate fate of the cosmos itself. Part 3. The expanding universe's betrayal. Space is expanding faster than light. So far, we've discussed how painfully slow light speed becomes when compared to the vast distances separating objects in the universe. We've examined how inadequate it is for exploring our galaxy, let alone reaching other galaxies. But there's something even more frustrating happening, something that makes the slowness of light speed not just disappointing, but cosmically unfair. The universe is expanding, and in many regions, it's expanding faster than light itself can travel. Now, this sounds like it directly violates Einstein's famous rule that nothing can move faster than light. You've probably heard that rule stated as absolute fact, the ultimate speed limit. Unbreakable. So how can space expand faster than light without breaking physics? Here's the crucial distinction that most people miss. Einstein's speed limit applies specifically to objects moving through space. Nothing with mass can move through space faster than light. No spacecraft, no particle, no signal, nothing. That rule remains absolutely true and unbroken, but space itself can expand at any rate whatsoever. Think of it like dots drawn on a balloon's surface. As you inflate the balloon, the dots move apart from each other. But here's the key insight. The dots themselves aren't actually moving, they're stationary relative to the rubber surface. What's moving is the rubber between them. It's stretching, expanding, growing. The universe works exactly the same way. Galaxies aren't racing through space faster than light. Instead, the space between them is expanding, carrying them apart like dots on an inflating balloon. And here's the part that keeps cosmologists awake at night. Due to something called the Hubble constant, which describes the rate of cosmic expansion, sufficiently distant galaxies are moving away from us faster than the speed of light, not through space, but because the space between us and them is expanding so rapidly. What does this mean in practical terms? What are the real consequences? It means there are galaxies in the universe that we can observe through our most powerful telescopes. Galaxies we can see, photograph, study, analyze, but we can never, ever reach. Not even at light speed. Not even if we started traveling toward them right now. Even if you pointed yourself directly at one of these distant galaxies and somehow achieved light speed instantly, traveling without rest at maximum velocity, you would never arrive. Not in a million years. Not in a billion years. Never. Why? because the space between you and that galaxy is expanding faster than you're moving forward through it. You'd be like someone on a treadmill set to run faster than their maximum running speed. You're sprinting forward as fast as physically possible. Your legs are pumping. You're giving maximum effort, but you're still moving backward relative to your destination. The treadmill's speed exceeds your running speed. In the cosmic version, you're traveling forward at light speed, but space itself is expanding even faster, so the galaxy keeps receding away from you despite your movement toward it. You'd be flying forward and falling backward simultaneously. Think about how fundamentally unfair that is. Imagine seeing a destination clearly, knowing exactly where it is, being able to observe it in detail, but being physically incapable of ever reaching it no matter what you do. That's the situation we face with distant galaxies, the cosmic horizon, an unreachable boundary. This expansion phenomenon leads us to one of the most profound and genuinely disturbing concepts in all of cosmology, the cosmic horizon, also sometimes called the cosmic event horizon or the cosmological horizon. The cosmic horizon represents the boundary beyond which we can never receive information. Never, not difficult to receive, not expensive to receive, impossible to receive. It's determined by the interplay between how fast light can travel toward us versus how fast the universe is expanding and carrying distant objects away from us. Currently, astronomers have calculated that the cosmic horizon sits approximately 16 billion light-years away from Earth. Any galaxy currently farther than 16 billion light-years from us is moving away faster than light due to cosmic expansion. Even if that galaxy aimed a perfectly focused beam of light directly at Earth, today a laser pointed straight at us, that light would never reach us, ever. The space between us and them is expanding too rapidly. The light would be traveling toward us, absolutely, but the space it's traveling through would be expanding faster than the light is moving. So the light would actually be getting farther away from Earth, even while racing in our direction at maximum speed. This means the observable universe, everything we can theoretically see with perfect telescopes, is not the same as the reachable universe, everything we could theoretically travel to. The observable universe measures approximately 93 billion light-years across. That's how far light has been able to travel while accounting for cosmic expansion. That's the region of space from which light can reach us. But the reachable universe, the portion we could actually visit, even with perfect light speed travel, it measures roughly 16 billion light-years across. And here's the terrifying part. It's shrinking. Every single second, galaxies that were previously reachable cross the cosmic horizon and become forever unreachable. Right now, as you process these words, galaxies are slipping away into permanent inaccessibility, not because they're moving through space, but because the space between us and them is expanding. Think about that for a moment. Really contemplate the implications. The reachable universe is actively getting smaller. The universe isn't just vast, it's becoming more vast, more empty, more lonely with each passing moment. And this process is accelerating, getting faster. The expansion of the universe isn't constant or steady, it's speeding up. This acceleration is driven by something scientists call dark energy, which comprises approximately 68% of all the energy in the universe, but which we barely understand at all. We know it exists because we can measure its effects. We can observe distant supernovas and calculate that the universe's expansion is accelerating, but we have almost no idea what dark energy actually is. It's one of the biggest mysteries in physics. As the expansion accelerates, the cosmic horizon gets closer to us. More and more of the universe becomes unreachable. The accessible portion of space contracts. Trillions of years from now, if humanity or some other intelligent species still exists, if consciousness somehow persists through the heat death of stars and the decay of matter, those future beings will look out at the universe and see almost nothing. The galaxies will have expanded away so far and so fast that their light can no longer reach us. Future astronomers will observe a dark, empty universe with only our local group of galaxies visible. Even those will have merged into a single, massive galaxy by then. They might not even know other galaxies exist beyond their local cluster. They might believe the universe consists solely of their small group of merged galaxies surrounded by infinite darkness and nothing else. All evidence of the greater cosmos will have literally disappeared beyond the cosmic horizon. We live in a privileged time. Cosmologically speaking, we can still see a universe filled with hundreds of billions of galaxies. We can observe the cosmic microwave background radiation from the Big Bang. We can study the large-scale structure of the universe. But that window is closing. Slowly, yes, but inevitably. The universe is showing us its wonders now, in this epoch, knowing we can never touch them. And eventually, it will stop even showing them. It will pull down the curtain and leave future civilizations in darkness. Compare this to human exploration on Earth. When ancient sailors wondered what lay beyond the horizon, they could build ships and find out. When early aviators wondered what lay beyond the clouds, they could build planes and discover. When mid-century scientists wondered what lay beyond Earth's atmosphere, they could build rockets and explore. But cosmic horizons are different. They're not challenges to overcome with better technology. They're fundamental limits imposed by the structure of space-time itself. No technology, no matter how advanced, can overcome them. They're walls built by the universe itself. Dark energy and accelerating expansion. Let's dig deeper into this dark energy phenomenon, because it's crucial to understanding why light speed becomes increasingly inadequate over time. In the late 1990s, two teams of astronomers studying distant supernovas made a shocking discovery. They were trying to measure the rate at which the universe's expansion was slowing down. Everyone assumed expansion was decelerating, that gravity was gradually slowing the universe's growth. Instead, they discovered the opposite. The expansion was accelerating, getting faster. This discovery won the Nobel Prize in Physics in 2011 because it fundamentally changed our understanding of the cosmos. And it created a massive problem. What could possibly be driving this acceleration? Gravity attracts. It pulls things together. All the matter in the universe, stars, planets, gas clouds, dark matter. Everything should be working to slow the expansion through gravitational attraction. But something was overpowering gravity. Something was pushing the universe apart with increasing strength. Scientists named this mysterious force dark energy because we have no idea what it actually is. Dark doesn't mean invisible to light. It means unknown, mysterious, completely baffling. Here's what we know about dark energy. It comprises approximately 68% of all energy in the universe, more than 2/3 of everything. The majority of reality consists of something we don't understand. It exerts a kind of negative pressure that drives cosmic expansion. Unlike gravity, which attracts, dark energy appears to repel or push. It's distributed uniformly throughout space. Unlike matter, which clumps into galaxies and clusters, dark energy seems to exist everywhere equally. Its density appears to remain constant as space expands. This is weird. As the universe grows, you'd expect energy density to decrease. There's more space for the same amount of energy. But dark energy doesn't work that way. As space expands, more dark energy appears, maintaining constant density. Here's what we don't know about dark energy. What it actually is. Is it a property of space itself? Is it a new kind of field? Is it something else entirely? We have no idea why it has the specific strength it does. Why 68%? Why not 90% or 10%? The value seems arbitrary. Whether it will remain constant forever. Maybe it will strengthen. Maybe it will weaken. Maybe it will suddenly change entirely. We don't know. This uncertainty makes predicting the universe's distant future extremely difficult. We can project current trends, but if dark energy changes behavior, all bets are off. What does accelerating expansion mean for light speed's adequacy? It means the cosmic horizon is getting closer. Galaxies that are currently reachable will become unreachable. The accessible universe is shrinking. It means the observable universe and the reachable universe are diverging. We can see more than we can ever reach, and that gap is widening. It means that even if we developed light-speed travel tomorrow, we'd have a limited time window to reach distant destinations before they slip beyond the cosmic horizon forever. There's a ticking clock on cosmic exploration. Not because our technology is insufficient, though it is, but because the universe itself is running away from us faster than we can chase it. Light travel time versus universe age. The fundamental problem. Now let's examine why light speed is fundamentally, unavoidably, tragically slow compared to the universe's actual structure. This gets at the heart of the problem in a way that's both mathematically precise and emotionally devastating. Light has been traveling through space since the Big Bang occurred 13.8 billion years ago. That's the maximum time light has had to propagate through the universe. In that time, light from the most distant visible galaxies has traveled approximately 13.8 billion light-years to reach us, right? That seems logical. If light travels for 13.8 billion years, it should cover 13.8 billion light-years. But remember, the observable universe measures 93 billion light-years across. How is that possible if light has only been traveling for 13.8 billion years? How can the universe be wider than light could have traveled in the universe's entire existence? Because the universe expanded massively while the light was traveling. Those distant galaxies emitted their light 13.8 billion years ago, when they were much, much closer to us, perhaps only a few 100 million light-years away. But during the billions of years that light spent traveling toward us through space, the universe expanded enormously, pushing those galaxies much farther away. So by the time the light finally reaches Earth and enters our telescopes, the galaxies that originally emitted it are now approximately 46.5 billion light-years away. That's the radius of the observable universe. The light shows us where those galaxies were, but they're not there anymore. They've moved. Or rather, space has expanded and carried them much farther away. Here's what this means practically. Even if you traveled at light speed toward a distant galaxy you observe through telescopes, you couldn't reach it. By the time you arrived at where that galaxy was when it emitted the light you see, that galaxy would be much farther away than when you started. You'd be chasing an ever-receding target, like trying to catch someone who starts running away from you the moment you begin pursuit, and who runs at exactly your running speed or faster. You can never catch up. You can never get closer. The gap remains constant at best, or, more likely, increases. It's like watching a movie of a place that no longer exists. The light from distant galaxies is historical footage showing us ancient history. When we observe a galaxy 10 billion light-years away, we're seeing it as it appeared 10 billion years ago. We're seeing the past. That galaxy might not even exist anymore in its current form. And this gets to the absolute heart of why light speed is so painfully slow. The universe is not just large, it's large and expanding dynamically. If the universe were static and unchanging, light speed would still be frustratingly slow, but at least, given enough time and patience, you could theoretically reach anywhere you could observe. Distance would be an obstacle, but not an impossible barrier. But in an expanding universe, particularly an accelerating, expanding universe, there are places you can see right now, clear as day through telescopes, that you can never reach, regardless of how fast you travel. There are destinations that are forever beyond the cosmic horizon, no matter what you do. Light speed isn't just slow, it's insufficient, inadequate, fundamentally incapable of allowing us to explore most of the universe we can observe. And unlike human limitations that we might overcome through technology, lack of food, water, air, radiation protection, propulsion, this limitation is built into the structure of reality itself. It's not an engineering problem, it's a physics problem, a universe problem. Even if we achieved light-speed travel tomorrow, through some miraculous breakthrough, we'd still face the same fundamental issue. Most of the universe is running away from us faster than we can chase it. The universe gave us eyes capable of observing vast cosmic distances. It gave us telescopes to see even farther. It revealed billions of galaxies containing trillions of stars. It showed us wonders beyond imagination. And then it made certain we could never touch any of it, never visit, never explore directly, never make contact with whatever civilizations might exist on distant worlds. We're observers in a cosmic museum where almost everything is behind unbreakable glass. We can look, but we cannot touch. We can study, but we cannot experience. We can wonder, but we cannot know for certain. Is this design? No, almost certainly not. The speed of light emerges from fundamental properties of electromagnetism and space-time. The universe's expansion follows from the initial conditions of the Big Bang and the properties of dark energy. These are consequences of physics, not intentions. But the effect is the same as if it were deliberately designed to frustrate us. We're trapped in our tiny corner of space-time, able to observe wonders we can never reach, tormented by knowledge of cosmic beauty forever beyond our grasp. We can see paradise, but we're separated from it by an uncrossable gulf of expanding space. So when people ask, why haven't we found aliens, or why don't we see evidence of galactic civilizations, part of the answer might simply be, light speed is too slow and space is expanding too fast. Even if the galaxy contains millions of civilizations, even if they're broadcasting signals constantly in all directions, those signals travel at light speed. They take centuries or millennia to reach us across interstellar distances, and by the time we receive them and send a response, those civilizations might have evolved beyond recognition, migrated elsewhere, or ceased to exist. The universe isn't just vast, it's vast and getting vaster. It's not just old, it's old and getting older, and the gaps between everything, between stars, between galaxies, between civilizations are widening with each passing moment. Light speed isn't the solution to exploring the cosmos. In the universe we actually inhabit, at the scales that actually matter, light speed is barely faster than standing still. And things are about to get even more personal, because now we need to confront what all of this means for humanity specifically. What does it mean for our future, our survival, our dreams of becoming a spacefaring species? The answers aren't encouraging, but they might be illuminating in unexpected ways. Part 4. The Humanity Perspective. What light speed means for human exploration. Let's bring this cosmic nightmare back down to human scales. Let's make this personal, because abstract discussions about cosmic horizons feel disconnected from real life. But when we talk about what this means for humanity's future, suddenly it becomes very real. Imagine humanity somehow invented a light-speed spacecraft tomorrow. Perfect engineering, no fuel concerns, instant acceleration, pure science fiction, completely impossible. But let's explore the scenario. What could we actually accomplish? Within a human lifetime, 80 years, you could reach any star within 80 light years of Earth. That's approximately 2,000 stars, less than 0.001% of the galaxy, 1,000th of 1%. You could send one-way colony missions to nearby star systems. The colonists would never return home, never communicate in real time with loved ones, never see Earth again. You could establish maybe 50 to 100 colonies maximum, dedicating every resource to this goal. Within recorded human history, 5,000 years. You could reach stars up to 5,000 light years away and explore maybe 10 million stars, roughly 0.01% of the galaxy. Within Homo sapiens' existence 300,000 years. You could finally explore the entire Milky Way and even reach nearby galaxies like the Large Magellanic Cloud. But here's the crushing problem. Even these timescales are impossibly long for individual humans. Unless we solve aging through radical life extension, cryogenic sleep, or mind uploading all currently fictional no individual could participate in interstellar exploration beyond very nearby stars. You'd need generation ships. Vessels where the departure crew isn't the arrival crew. Children born in space, living entire lives aboard the ship, dying without ever reaching the destination. For trips longer than 80 years, you'd need multiple generations. For trips of centuries, you'd need entire civilizations living aboard ships. And this assumes light speed, the theoretical maximum, with our current fastest spacecraft Voyager 1 at 38,000 miles per hour. We're traveling at 0.006% of light speed. At that real-world rate, reaching Proxima Centauri would require 73,000 years, 7 times longer than recorded human history. By arrival, humanity might have evolved into a different species entirely. Generation ships, the brutal reality. Generation ships represent the only realistic option for interstellar travel at sublight speeds. But let's think through the practical realities. You'd need thousands of people minimum to avoid genetic problems across generations. Maybe 10,000 or more. You'd need completely self-sustaining ecosystems, perfect recycling of air, water, waste, agriculture for food, manufacturing to replace broken equipment, everything to maintain civilization for centuries without external support. You'd need to maintain technology and knowledge across generations when the designers died generations ago. You'd need to maintain social cohesion when people are born, live, and die in a metal box, never seeing their destination. You'd need to handle psychological problems. Humans evolved for planetary surfaces with open skies. What happens to minds born and raised in corridors and compartments? The engineering challenges are staggering. Materials withstanding cosmic radiation for centuries. Propulsion accelerating millions of tons. Shielding against micrometeorites, impacting with nuclear weapon level energy. Compare this to Earth exploration. Europeans crossing the Atlantic took weeks or months, difficult but survivable within one lifetime. Moon missions took days, but interstellar travel, the explorers who depart would never return. Never report back except through radio signals taking years or decades to reach Earth. Imagine saying goodbye to Earth forever. To friends, family, blue skies, oceans, forests, committing yourself and descendants to life in a metal container for 500 years so distant grandchildren might see a new world. Would you volunteer? Would you have children knowing they'd be born into that existence without consent? These aren't just engineering problems. They're ethical, psychological, and philosophical problems with no clear answers. The psychology of cosmic insignificance. There's something psychologically devastating about truly understanding how slow light speed is at cosmic scales. It forces you to confront humanity's cosmic insignificance directly. We live on one planet among billions, orbiting an average star among hundreds of billions, in an average galaxy among hundreds of billions or trillions. Even traveling at the cosmic speed limit, we'd still be trapped in a microscopic bubble of space. We can see billions of galaxies through telescopes. We can never visit any of them, ever. We can detect planets around other stars and speculate about alien life, but we can never meet those civilizations if they exist. Some philosophers call this the Fermi paradox or the Great Silence problem. If the universe contains so many planets, where is everybody? Maybe the answer is simple. Light speed is too slow, space is too big, the universe is too empty. Even if our galaxy teems with civilizations broadcasting constantly, those signals travel at light speeds, taking years, centuries, millennia to reach us. By the time we receive signals and respond, those civilizations might be gone, destroyed themselves, evolved beyond recognition, or simply lost interest. The speed of light isn't just a physical barrier. It's a barrier to contact, communication, connection. We might live in a universe full of intelligent life, yet we're fundamentally isolated from almost all of it. Some find this depressing. We're alone, trapped, insignificant. Others find it liberating. We're free to make our own meaning. Either way, light speed's inadequacy forces psychological reckoning with our place in the universe. Light speed as a communication barrier. Even if we never achieve interstellar travel, we might hope to communicate with other civilizations through radio or laser signals, but light speed makes even that vastly more difficult than people realize. The nearest star is 4.24 light-years away. A message exchange takes 8.5 years minimum. Realistically, much longer. A realistic conversation with Proxima Centauri. Year 0, we send a message. Year 4, they receive it. Years 5 to 10, they decode, debate, compose response. Years 14 to 19, we receive their response. Nearly 30 years for 3 exchanges. And that's the nearest star. 4 stars 10 light-years away, 20-year one-way delays. 4 stars 100 light-years away, conversations taking centuries. 4 stars across the galaxy, millennia. Imagine maintaining any relationship across those timescales. By the time you receive responses, you might be dead. Your civilization might have changed dramatically. Your language might have evolved. Your reasons for contact might be forgotten. Light speed slows down everything. Every interaction, every relationship, every possibility of connection. By the time signals cross space, civilizations could rise and fall. Languages could emerge and go extinct. Technology could advance beyond recognition. You couldn't have conversations, negotiations, trade ideas in real time, establish relationships, or collaborate. Everything would be asynchronous, delayed, uncertain. This is why the universe feels empty, even if it's full of life. Millions of civilizations could be broadcasting constantly, but signals take so long to propagate that by the time we receive them, the senders might be extinct. We might receive messages from civilizations that destroyed themselves thousands of years ago. Their signals continue outward like echoes from the dead, or we're surrounded by signals still in transit, decades or centuries from reaching Earth. The universe could be full of voices calling out, and we're all too far apart to hear each other in time to matter. Light speed isn't fast enough for travel, communication, connection, or the cosmic community science fiction imagines. We're alone not because we're the only intelligent species, but because the universe is too big and light is too slow, and that isolation might be permanent not from lack of will or technology, but because the universe's fundamental structure makes connection essentially impossible. So what does all this mean? What should humanity do with this knowledge? The final section will explore those questions and offer perspectives on our place in this vast, unreachable cosmos. Part 5. The final perspective and conclusion. Why the universe seems designed to be unreachable. Some physicists have noticed something peculiar about the speed of light. Something that feels less like coincidence and more like cosmic irony. It's fast enough that we can observe the universe. The night sky reveals countless stars and galaxies. Light reaches us from billions of light years away, providing an extraordinary window into cosmic history. But it's slow enough that we can never reach most of what we observe. The speed of light sits in this specific range that gives us knowledge without granting access. We can see, but not touch. We can observe, but not explore. We can wonder, but never know for certain. If light speed were 1,000,000 times faster, the universe would become much more accessible. We could visit nearby stars in days instead of years. We could explore the galaxy in centuries instead of millions of years. We could reach Andromeda in thousands of years rather than millions. If light speed were 1,000 times slower, we wouldn't observe much of the universe at all. The night sky would appear darker and more limited. We wouldn't know about other galaxies or the cosmic web's vast structure. But the actual speed of light seems almost perfectly calibrated to give us knowledge without accessibility. We can see the universe's wonders through telescopes. We can photograph distant galaxies, analyze their composition, study their formation. We can observe cosmic history unfolding. But we cannot reach those places, cannot visit those galaxies, cannot explore those worlds. It's like being shown a detailed map of paradise, given perfect binoculars to observe it, and then being told you can look but never visit. Is this by design? Almost certainly not. The speed of light emerges from fundamental constants, the permittivity and permeability of free space. These are consequences of physics, not intentional choices. But the effect feels exactly the same as if it were deliberately designed. We're trapped in our corner of space-time, given the ability to see wonders we can never reach, tormented by knowledge of cosmic beauty forever beyond our grasp. No intention, no purpose, no design, just the blind mechanics of physics creating a cosmos where intelligent beings can observe vastly more than they can ever reach. The numbers that break your brain. Let's end with some numbers that truly drive home just how devastatingly slow light speed is at cosmic scales. Numbers so large they stop feeling real. Numbers that your brain simply cannot process in any meaningful emotional way. But try anyway. Really try to comprehend these figures and what they mean for humanity's cosmic future. The Milky Way galaxy. Diameter 100,000 light-years. Time to cross at light speed 100,000 years. Number of stars 100 billion to 400 billion. Percentage you could visit in a human lifetime at light speed 0.00001%. That's 5 zeros after the decimal point before you hit a 1. To put that in perspective, if you lived 80 years and could travel at light speed, you could visit 80 stars out of hundreds of billions. You'd have explored 0.000002% of the galaxy. That's not even a rounding error. That's less than a rounding error's rounding error. The local group of galaxies. Diameter, 10 million light-years. Time to cross at light speed, 10 million years. This duration is longer than humans have existed as a species by a factor of 33. This is 25% as long as complex life has existed on Earth. Modern humans appeared roughly 300,000 years ago. 10 million years is over 30 times that entire span. If Homo sapiens had somehow achieved light-speed travel the moment our species first appeared, and our civilization had remained stable and committed to exploration for our entire existence as a species, we'd only be 3% of the way across the local group by now. The Virgo supercluster. Diameter, 110 million light-years. Time to cross at light speed, 110 million years. This is longer than mammals have existed on Earth. This is approximately the time since dinosaurs first appeared. This is roughly 1/4 of the time since complex multicellular life emerged. The first dinosaurs appeared about 230 million years ago. Modern mammals didn't emerge until about 66 million years ago after the dinosaur extinction. Even these vast biological timescales barely approach what would be needed to cross a single supercluster at light speed. The observable universe. Diameter, 93 billion light-years. Time to cross at light speed, 93 billion years. The universe itself is only 13.8 billion years old. This journey would take nearly 7 times longer than the universe has existed. This journey is literally impossible. Even in principle, even if you had started at the Big Bang. Let that sink in completely. Even if you had started traveling at light speed at the exact moment of the Big Bang, and traveled continuously without rest for the entire age of the universe, 13.8 billion years, you would only be about 15% of the way across the observable universe. The universe expanded faster than you could cross it, even at maximum possible speed, even if you had all the time that has ever existed. Number of galaxies in the observable universe, 200 billion to 2 trillion. The exact count remains uncertain because our telescopes have limits, and many distant galaxies are too faint to detect reliably. But conservative estimates suggest at least 200 billion galaxies. More recent estimates push that toward 2 trillion. Number of galaxies you could reach in a human lifetime at light speed, 0. Not approximately 0. Not effectively 0. Exactly 0. The nearest major galaxy, Andromeda, sits 2.5 million light-years away. A human lifetime lasts 80 years. You'd need to live 31,000 times longer than a normal human lifespan just to reach our nearest galactic neighbor. Percentage of the observable universe that is currently reachable, even at light speed, approximately 2%. Due to cosmic expansion and the cosmic horizon, only about 2% of the observable universe remains theoretically reachable even if you had perfect light speed travel, and that percentage shrinks every second as more galaxies cross the cosmic horizon. Percentage of the observable universe that will remain reachable in the far future as cosmic expansion accelerates, approaching 0%. As dark energy continues driving accelerating expansion, the cosmic horizon draws closer. Eventually, trillions of years from now, only our local group of gravitationally bound galaxies will remain accessible. Everything else will have receded beyond the horizon. the reachable universe will contract to an infinitesimal fraction of what we can currently see. Average distance between stars in our galactic neighborhood, 5 light-years. Even our immediate stellar neighbors, the ones we consider nearby, sit years apart at light speed. The galaxy isn't a crowded place. It's a vast, mostly empty void, with tiny islands of matter scattered impossibly far apart. Fastest speed ever achieved by a human spacecraft. Approximately 0.06% of light speed. The Parker Solar Probe, using gravitational assists from the Sun, has reached speeds around 430,000 miles per hour. That sounds incredibly fast. It's not even 1,000th of light speed. At that velocity, reaching Proxima Centauri would require over 6,500 years. Number of stars humanity could realistically reach with current technology in 100 years, 0. With our current propulsion methods, we cannot reach even a single other star system within a century, not one. The nearest star requires thousands of years of travel with existing spacecraft. The cosmic speed limit is too slow, so here's the final, inescapable truth that we must confront. Light speed 186,282 miles per second. The cosmic speed limit, the fastest anything can possibly travel, according to the laws of physics, is too slow for the universe we actually inhabit. At cosmic scales, light speed becomes incredibly, annoyingly, frustratingly slow, according to Universe Today. It's glacially slow for interstellar travel, according to Scientific American, making even our nearest stellar neighbors require years to reach at maximum possible speed. It's too slow to explore our galaxy in human timescales. Even at light speed, crossing the Milky Way would consume 100,000 years. That's 10 times longer than human civilization has existed. 5 times longer than agriculture has existed. Longer than Homo sapiens have existed as a species. It's too slow to reach other galaxies in the lifetime of civilizations. The nearest major galaxy requires 2.5 million years to reach at light speed. Civilizations rise and fall in thousands of years. Languages evolve beyond recognition in centuries. Technologies transform societies within decades. Nothing humans have ever built has lasted millions of years. It's too slow to cross the observable universe in the age of the universe itself. Even starting at the Big Bang and traveling continuously at maximum speed for 13.8 billion years, you'd only traverse 15% of the observable universe's current size. The universe grew faster than light could cross it. The universe is vast, unimaginably, incomprehensibly vast, and the maximum speed allowed by the laws of physics is completely, utterly inadequate for the scale of what exists. This is either the cruelest joke nature has ever played, or the most profound lesson existence has to teach us. Philosophical acceptance and the message. Maybe light speed's slowness teaches us humility. The universe will always be mostly beyond our reach. Regardless of how advanced our technology becomes, we're accustomed to conquering challenges. Humans have crossed oceans, climbed mountains, flew through air, traveled to the moon, but cosmic distances represent a different category of limitation. This isn't a challenge to overcome with better engineering. It's a fundamental constraint built into reality itself. The speed of light isn't slow because we haven't invented better propulsion. It's the maximum speed possible because of how causality works, how time and space relate. We cannot overcome this any more than we can make 2 + 2 = 5. It's not a technological problem. It's a reality problem. Or maybe light speed's inadequacy teaches us patience. We live in an era of instant gratification and immediate results. But the universe operates on timescales that make human lifetimes look like eye blink. Stars take millions of years to form. Galaxies take billions of years to evolve. The cosmic web took the entire age of the universe to develop. The universe isn't in a hurry. Maybe we need to adjust our expectations and start thinking in terms of millions or billions of years. Or maybe light speed's slowness is telling us something more important. Look closer to home. We're so focused on what's out there that we forget to appreciate what's right here. We live on a planet with billions of years of evolutionary history, millions of species, countless ecosystems, breathtaking landscapes we've barely begun to understand. We're part of a solar system with dozens of moons and worlds we've barely explored. Mars remains largely unmapped. Europa's subsurface ocean remains uninvestigated. Titan's methane lakes remain unstudied. We're surrounded by questions about our own origins, consciousness, and existence that remain unanswered. Maybe the slowness of light speed isn't a barrier. Maybe it's a message. Explore where you are. Understand what you have. Take care of the world you can actually reach. Because the rest of the universe, vast, beautiful, filled with wonders, will always be there. Gleaming in the darkness, impossibly far away. Light speed is slow. The universe is large. Space is expanding. And we're here, in this moment, in this place, on this place blue dot. Witnesses to a cosmos we can observe but never fully explore. Maybe that's not a tragedy. Maybe that's exactly how it should be. Maybe our purpose isn't to conquer the cosmos, but to appreciate it. Not to possess the universe, but to understand our place within it. Not to reach every star, but to care for the one we orbit. The universe gave us consciousness to observe it, intelligence to comprehend it, curiosity to wonder about it, and wisdom, perhaps, to accept that observation and wonder might be enough. We'll never walk on distant worlds orbiting other stars. We'll never meet alien civilizations in other galaxies. We'll never traverse the cosmic web, but we can look up at the night sky and know what we're seeing. We can point telescopes at distant galaxies and understand what we're observing. We can calculate cosmic distances and comprehend the scale of existence. Where the universe become conscious of itself, atoms arranged to contemplate atoms, star stuff pondering stars. Light speed is too slow. And maybe that's okay, because we're already exactly where we need to be.